Welcome, everybody. I hope you have enjoyed PDC so far. I'm very excited and thrilled to be here today and talk about Axum. This is on a series of talks called From the Labs, which means that these are things that we're not necessarily saying that we're going to be releasing soon. In fact, some of these things we're talking about may never come out in a product at all. I just want to caution you about that. But it gives us an opportunity to talk about some of the more forward-looking and perhaps longer-term things that we're thinking about and give you an insight into that and give you an opportunity to provide us with feedback on the things we're thinking about. I hope you can excuse I have a little bit of a cough this morning. It's not the flu, though, so I'm not going to pass it on to you. Axum refers to, I don't know if you know this, but Microsoft code names for things that haven't shipped yet are always geographical locations. Axum refers to a small town in northern Ethiopia. It's a UNESCO World Heritage Site. All right, I'm going to talk about a looming problem. If we're extrapolating the current hardware trends, currently we're dealing with, we all have at least dual cores. Most of us have quad cores or 8 cores. At work, at home, et cetera, et cetera. Even laptops are now dual cores or quad cores. If we extrapolate that hardware trend to its logical conclusion, which is where you, in a common place, have 32, 64 cores, or at least hardware threads at your disposal, then we're going to start running into trouble with the current programming practices. We're going to hit a glass ceiling on performance of parallel hardware. So the practices that we have today are not really sustainable, and we need to switch to new models. And that's going to take time. It's going to require rethink both on platform vendors, tools vendors, and the programmer community at large. It will take time, as I said, but we also need really strong tool support to cut down the costs of doing doing a paradigm shift. And the more we can leverage current technologies, obviously, we're going to reduce the cost of doing new things. So what's the problem? Sharing is typically a beautiful thing, or so we have been taught through our childhood and formative years. But in parallel computing, it's actually the source of all evil. The issue is this. We have a basic model where we have 3 threads or tasks that are just running along, doing their own thing, without really coordinating anything with each other. They're addressing a whole big bag of address space. It's just memory locations ultimately that they're manipulating, reading from and writing to. This is how they exchange data. This is how they communicate with each other. And they then synchronize via compare and swap in memory cells. They take locks to protect data. And this is the really odd thing. To protect data, we're really drawing boundaries around code. That's really what we're doing. We're not drawing any boundaries around the data. We're drawing the boundaries around the code, which is kind of putting the cart before the horse in many ways. So unpartitioned state is, and this is what our programs typically look like, our parallel programs typically look like today. It is a huge mess. We have unstated, indirect, subtle data dependencies. We have documentation that's quickly out of sync with reality in a conservative way or in a naive way. It could either be sort of overstating things or understating things. It requires enormous discipline to maintain the code, at least through revisions of it, several versions of it. And it's really a process scale issue. There's also a performance scale. And those of you, I don't know how many of you went to Igor's talk about P-Link right before this, but he talked about the issues of false sharing and how overlapping working sets between these tasks and threads really cause a performance bottleneck that you're not really seeing horribly at 8 cores or even perhaps 16 cores. But if you're going to be running on 100 processors, or you're going to run on 256 processors, you're definitely going to see a tremendous issue with cache coherence traffic, and it's just going to be an enormous problem for us. I'm going to focus on, when I talk about the motivation for Axum, I'm going to focus on the first issue, the process scale. But the approach that I'm suggesting will also address the technology scale. So, shared memory. We have implicit component dependencies, right? When two, and this is the key, they're implicit, right? They don't really, they're not expressed anywhere in the code, really, except in completely ad hoc fashions. So when two parallel components or more access a common address cell or memory cell like that concurrently, and at least one of them is a writer. Everything I'm going to talk about today is irrelevant if they're just reading, right? So at least one of them has to be a writer. Then there is an implicit component dependency between these two, right? They're both using the same address cell. How are we going to know that from looking at the code? Well, typically we don't, because we're addressing it through pointers or references in managed code. And we really don't know where they've come from, those references. We don't know where our pointers are or where they came from. So this is how we're going to depict that dependency. It's a narrow arrow for the implicit dependency. And as we try to leverage more and more cores, we're going to have to add parallel components, or we're just going to not scale at all. We're going to not go up to 4. If we don't go up to 4 cores, we're not going to be taking advantage of the next generation of hardware. And as the core count grows, we'll just continue this, right? We'll try to add more concurrency, and the complexity of our application and our implicit dependencies grows faster than the core count. And all we see is eventually a tangled mess of spaghetti. This is really the new spaghetti code. It's parallel shared memory code. And we can only wonder what's going to happen with it when it comes back in the next revision. Unless, of course, we don't care. So now, the reality of the situation is, of course, that it's not that bad. These implicit dependencies are the worst case. But we can't know that from looking at the code. So what do? Well, if we're very well disciplined, we start out a project like this by writing down the actual dependencies, and then writing rules for how we develop code and how we pass data between these components so that we actually have an idea of what the reality is. So we put that in a document. And it is, for anything of any complexity that's interesting, it's going to be a long document. And we're going to quickly invalidate it by fixing bugs or versioning it in some other way. Okay? And only the very strongest, I claim, only the very strongest engineering organizations have the discipline in place to prevent this from ever happening. Okay. So what is the answer? Well, one answer that I'm going to suggest is productive and has some of the keys here, is a system that we all know of that is running on a huge number of processors today. It's programmed by legions of programmers in disparate organizations, in different organizations. It scales well, it's robust, and probably has something to teach us, and it's the web. Right? It is really a parallel system or parallel application of enormous scale, and it works. It works. So what are the principles? Well, it's loosely coupled. Right? One party doesn't know much about the other parties. It's hard to take dependencies that are implicit even if you can't reach the other party. Components don't trust each other. You know, unless you authenticate yourself and you have a business relationship of some form, maybe it's a credit card or something else, right? But you have to have some relationship that gives you trust. Otherwise, there is absolutely no trust between components. You have partition state. My website doesn't share its data with your website. It doesn't, right? We have some things that we pass in messages between us, but I don't give you access to my database tables, at least if I know what I'm doing. Right. So partition state really holds one of the keys. And I'm going to talk about all those four components of the web programming model. That's interesting, but I'm going to focus primarily on 2 of them. Partition state is one of them. And this is the exact same diagram we had earlier, except we draw boundaries around some of these components. So we increase the grain of our components, if you will, a little bit. And then we're starting to draw these broader arrows, and I use them to signify explicit dependencies. One where I state directly what the components need from each other and how they interact with each other. Okay? I then prevent the implicit dependencies from ever even being possible between the components. So they can't access each other's memory cells. Now, I'm still allowing some parallelism on shared memory inside the components, but I've essentially employed a divide and conquer strategy to it. So I've reduced the overall complexity of my problem. And now, this is really no different from modularization that we've done for at least 25, 30 years in programming. It's just that it's not about protecting fields and not about protecting internal class data. It's about where did I get my references from? And particularly with managed code, but it's true certainly in C++ also, that a lot of the data that you pass between components is reference data, not primitive data like integers or strings or floats. And when you are passing references, you are sharing data between components. There's just no two ways about that. So the solution here between components is to use message passing. And message passing is essentially a form of saying, I'm going to exchange data in very well-defined, explicit patterns. I'm going to either copy my data. I'm going to only send immutable data. I can send that by reference. That's completely safe, because then I don't have any writers. Or I'm going to transfer the ownership. I'm going to say, I give you this reference, or I give you this piece of data, and I'm giving up any reference to it. I'm not going to hold on to it. That's kind of hard sometimes to do that properly, but it certainly can be done. And one interesting aspect of message passing is that synchronization between components really is just a special case of data exchange. There's no need to take locks. There's no need to use barriers. There's no need to use semaphores or anything like that. You just do message exchanges, and that is how your components synchronize their actions. All right. Now, to really leverage message passing, however, and use it as a source of concurrency, which means that we have more parallelism than we would otherwise have, we need to deal with the fact that message passing needs to be asynchronous. And asynchronous is a can of worms, literally. Right? It's going to be extremely intrusive on your code. It's going to pop, even if you just say, oh, I'm just going to use asynchrony down here when I'm reading a file or I'm doing network I/O or whatever it is that I'm doing. It is going to bubble all the way up to the top frame of your architecture. It just is. Because if you're waiting anywhere, if you're blocking, waiting for results anywhere, you're holding on to the thread. And that is the issue with synchronous interactions, is that you're not freeing up resources. All right, we'll talk about that more, those practical aspects of it more later. But so that's sort of a technology scale issue, that you're holding on to resources. But you're also at a programming model level, if you're not doing things asynchronously, you are giving up. You're leaving money on the table in terms of performance, because you're not doing things in parallel that you could have. Now, it's intrusive. I said it's hard. It's really extremely complicated sometimes. We have a number of framework-based solutions to deal with designing programs that leverage asynchrony. We have, for example, the asynchronous programming model in .NET. I call that asynchronous because of the central interface that is used there. We have from the robotics team, we have a package called CCR, which takes a different approach to it based on queuing. There's this thing called promises. There's something called futures. We have data flow networks. Events have been there in .NET and prior to that for a long time. They're all framework-based, and they're all helpful, but they don't make it less complex. in many ways, right? Because it's still intrusive, it still bubbles all the way up, and if you do it, if you use any of them, it will impact your entire code. Okay, or actually everything above it, right? Not anything below it. All right, so the premise of Axum is that to do this, you need new practices, right? We just said that, but you need new languages, or at least new language features. And the issue is that libraries are good at enabling you, but what you really need is to be constrained. You need to be told no. It's kind of like my going to grandma for help with a problem that I have, when I really am feeling good about it afterwards, when what I really need is my mother's help, right? I need to be told what's right or what's wrong, and I'm not going to get that from libraries. But I can get that from compilers and languages. I need help with the formalism of state partitioning, like we talked about, and I need help with asynchrony. Okay, so Axum focuses on those two. I call Axum a special purpose language, and what I mean by that is that I don't at all expect you to write an entire application in Axum. I expect you to continue to use VB or C#, or now with VS 2010, there's an excellent new language, F# that you can also use. Those I expect you to be using for the bulk of the code. It's really, when we're drawing the boundaries at that outermost component level, that's when I expect you to use Axum. So what does it do? It partitions data into domains. Domains are those big boxes with broad arrows between them. And then we have the little boxes within the big boxes, and we call them agents. And they manipulate shared state. So we're still doing shared state. We're not getting rid of shared state. We're not a pure message passing model. Agents manipulate shared state within domains, but they're doing it in a way that they declare how they do it, or the compiler can infer what they do with the shared state. And you don't actually have to take any locks or do any synchronization. The runtime does it for you. So you are moving from a largely programmatic way, using locks and mutexes and barriers and whatnot, to a declarative model. Now, agents then communicate between domains. So you use message passing to communicate. Everything that passes between domains is via message passing. And this goes, and just to give you an idea of what we have to do to prevent you from circumventing that, agents in domains do not have access to statics in any class or global data in any way, right? Because that would be an escape hatch from this. So it's being strict and kind of anal about that. All right. And then Axum adds support for asynchrony and data flow. And I'll go into data flow a little bit later. The four main concepts of Axum. There's just four. Okay? And we can get by with three of them. The first one, actually we can get by with two of them, but not in very interesting code. The first one is that of a domain. And whereas today's models, and domains is sort of an encapsulation of data, right? And whereas today's model is much like having an open door policy. You're welcoming your neighbors into your house all the time. You don't have any locks on the doors. What I'm saying is that what we really need to do, lock the doors, shut the windows, and buy a gun. And I'll talk about the gun later, right? Don't let anybody in, but have them tell you, put things in your mailbox, right? And you'll respond by putting letters in your mailbox, but you don't actually get to see anybody. It's a very antisocial programming model from that perspective, but it's safe, right? Agents, now that's me inside my house, talking via channels to other agents in their locked up house, right? It's kind of like what my son does. Instead of going out and seeing friends, he spends all his time in his room with Facebook, right? So it is an emerging social model anyway, and we can apply it to programming as well. Now, schema is kind of a form letter. It's a way of putting these letters, these things that you put in these channel mailboxes together, so that you can be sure that the postman will take them. Let me just moisten my throat. OK, so let's talk about channels first, because they're kind of fundamental. They're conduits for messages between agents. All right? They are the fundamental support for in-process and distributed messaging. And here's a beautiful thing about the programming model that Axum is proposing. Once you have isolation and you have message passing, you're a hop, skip, and a jump away from a distributed programming model. Right? So now, in order for this model to be applicable both in the small scale within a machine and across machines, across many node clusters and even wide area networks, all we need is to be efficient locally and efficient and capable remotely. All right? So channels is a indirection mechanism, if you will. It's an abstraction of message passing that allows us to have an efficient implementation for the local case and a capable implementation for the remote case. Channels use what we call ports as a communication vocabulary. They're really just kind of like events or messages, if you will. We send data to ports on channels. Oops, that's not what I meant to do. And ports have directions. So input ports go from a client. And by client, I mean everything is an agent, really, right? But a client is an agent that initiates a connection. And the servicing agent, or service, I'll call it, is the thing that responds to the connection. Okay, so the client sends to the servicing agent, on input ports. They're going into the agent that is servicing you, and responds on output ports. There's also something we call request-reply ports, and I'll show you that when I go to show you some code later, where the data is going in both directions, and it's kind of like more like a synchronous call. All right, agents are active components. Domains are passive. Channels are just like plumbing, right? Agents is where we put our control flow. That's where we put our logic that is moving the algorithm forward, if you will, right? They're very similar to threads. We've been talking at PDC last year and this year a lot about moving away from a threads-based model to a task-based model. And that's absolutely the right thing to do for fine-grained concurrency. But there's still a place for sort of long-lived, more thread-like constructs. And that's what agents are. But they're not threads in that they don't, and I really want to avoid calling them threads because threads they imply a certain programming model that is associated with sheer evil that we talked about before. They have limited access to shared mutable state, but they have access to it. And they send and receive via channels. Here's an example of just that. We'll take a look at ping pong in a little bit more detail soon. I'll show you a couple of things that are interesting over here. Sorry I can't do this. There's a thing called receive, right? There's a channel here. So the agent actually implements a channel. We'll talk about that later. And this little left arrow here is a send. Okay. Both receive and send are expressions. Okay. Connecting to an agent can be done in two ways. They can do it in one of two ways for each occurrence, of course. There's a loosely coupled way where I rely on a factory called a provider, communication provider. And this factory creates channel endpoints. I have a channel type that I supply to it, and I have an address. And this can be, addresses don't have to be strings. For all practical purposes, strings are great for addresses. And in this case, it would be a remote connection that I'm making because it says HTTP, and I don't want to use HTTP locally. The other method of creating a connection to an agent is tightly coupled. And by tightly, in this particular instance, I mean I know the type of the agent that I'm connecting to. Right? I'm not disassociated from that. And I'll show you exactly how all this works later. Create a new domain is a kind of a funky word. It's longer than it should be, but anyway, it is what it is. We have the agent type here, and the create a new domain is a factory method for agent instances. So both channel declarations and agent declarations are types. And to actually run any code, we need instances of them. And we create them by making connections. All right. The hello world of message passing, ping pong. Two components furiously sending messages back and forth without doing anything in between. And it's a kind of a silly example, but it can demonstrate some of the features that I want to talk about. We have here a channel with two channels, one called ping, one called pong. Signal is a type that we added in Axum, in the Axum runtime, because .NET doesn't have a good unit type, right? A type that has no actual values associated with it. And it's kind of like void, but you can't use void very usefully in .NET because you can't instantiate templates, for example, with void, which is unfortunate. And you can't create any values of it either. So we need a unit type. It's very important for messaging. Then we declare the agent and define a primary channel. What do we call a primary channel for the agent? It's the channel. Agents can have many channels, but it's the channel that it gets first contacted on, right? It's kind of like this reference versus other references. And in the body of the constructor, it's kind of interesting that we put so much a lot of the agent code will go in the constructor, but it's kind of its main method, if you will. We have here just a loop. We're just looping. While we're receiving the value true through ping, we're going to continue sending responses. So the idea here is when I send false, stop. OK. And for every ping I receive, I send a pong back. And pong here is one of those unit values that we talked about. And when I receive false, I'm done. And in the main agent over here, our main program, I'm actually creating the ping agent and then looping through sending 100 ping true values to ping, receiving the pongs, and then finally ending up with sending false. So this is our first message passing program. You didn't see any domains here. So the reason for that is that we didn't have any state to share because we didn't do anything interesting in this application. We just sent messages back and forth, right? There was no state for the agent to manipulate in any way, or either reading or writing it. So we don't need agents we don't need domains if our agents don't have any shared state to work on. But if they do, which they do in most interesting scenarios, then we can define domain state to be that which is shared by multiple agents. And the compiler is so strict about it that only the agents that are declared lexically within the domain that have access to that domain state. So there's going to be a tight coupling between the agents that are allowed access to the domain state and the domain. All right? We saw the use of addresses before, and we call this the agent being hosted within the domain. We saw the use of two methods of creating new agent instances. There was the tight coupling with create a new domain, and there was the other way, which used an address, right? So what it means is that we have a factory for agents in new domains. In other words, when we use that factory method, we get a new agent instance, and it's associated with a new domain instance. That's a good way of getting things started. You kind of can bootstrap things that way, right? But if we want to share data, we actually need to have a way of getting agents to be associated with existing domain instances because we want, otherwise they're just agents again, right? So we need to hook them together. And we do this by what we call hosting, using the hosting APIs. So this is an instance level hosting, whereas this lexical containment is a type level hosting, where we actually associate an address. Here, again, it's a string with a factory for agent instances of a particular type. Okay. And we don't see the details of what that looks like. And it's where domains and agents come together where all the magic happens. Right? Agents are declared as either writers. They update mutable state in the domain. Still, The only thing that they have access to is domain state and agent state. They cannot touch static data. So if they're writers, they write it. If they're readers, well, they read mutable data. They have access to mutable data, but they can't modify it. And there's also an agent type called no access, which means it has no access to any immutable domain state, but it does have access to constant or immutable domain state. Right? So this affects how they can run. Agent code is then scheduled in parallel based on these 3 classifications, right? And it's completely taken care of by the runtime. You don't get involved. You declare what they do, and then that's it. And the compiler helps you out. And we enforce this then. One writer, many readers within each domain. Between domains is completely free-threaded. And no access agents are also free-threaded. They don't need to coordinate anything with anybody except through message passing, right? Right, so now I'm going to switch over to a demo. When I get, by the way, how many here have downloaded the Axum bits? OK. 2 handfuls or so. When you first start up an Axum project, you'll have, and if it's not a class library, or not a library, but if it's a console application, it'll look something like this. You'll have a main agent that implements a particular channel that the runtime knows about, and that will start your program. You receive the command line rather than being passed it. Okay? So even such a thing as command line passing happens through messages, because the outside environment isn't part of your domain. It has to communicate with your domain through messages. All right, so what I'm going to do here is I'm going to build a distributed table. I'm going to use it both locally within my process, and I'm going to use it between processes over time here. To do that, I will start, and I'm going to cheat a little bit by bringing in code from the toolbox here. You seriously don't want to see me type, so I'm just going to do it this way and talk to it one piece by one piece. Well, first thing we need to do is we need to have a domain, right? That's where we're going to store our table data, and we're just going to store it in a dictionary. In this case, I'm not going to try to be fancy with doing templates or anything. I'm going to have string-to-string dictionaries here. All right? OK, I have a constructor for my domain. I'm going to be using that later. I need to be able to communicate with agents in this domain, so I need to define a channel. OK, it's a very simple channel. It has three things on it. It has a put. I can put things into the dictionary. Right? That makes sense. I have a get, so I can get things out of the dictionary. That makes sense. And I have a done, which really tells the agent that I'm communicating with from the outside that, OK, you can go away and free up your resources. I don't need to talk to you anymore. You can stop waiting for my messages. All right, that's the channel. It's very simple. I now need, so again, domains they're passive and they don't allow access to their data. So we need some active component inside the domain to be able to actually do anything. And that's this agent. OK, what does the agent do? Well, in this case, it loops forever, or so it may seem, right? It loops forever, receiving, and we're going to be passing the dictionary data on the put we saw here as a key value pair, right? In .NET 4.0, there's a tuple type that is more elegant to use here than this, but I wrote this for a previous version of .NET, so I'm not using that. Key value pair, and I need to declare this here because I'm going to receive the put payload from the put message on my primary. When I don't qualify the port name like this, it's because it's from the primary. Okay? Into this variable, and then I'm going to call put value, which actually does the work. I'm going to do the same thing with a get thing, where I'm only getting the key, of course. And I'm going to send back to, I'm going to get the value, and I'm going to send back here to key. And this is where request reply messages come in. If you see here, it actually has 2 types, a string coming in and a string going back. What I'm actually receiving is a little temporary mini port that I can use to send responses back on. Okay? So that's what I'm getting there. And then after I receive done, I'm done. I can just return from this function. Interesting to notice that I'm doing all my work in the constructor, right? Constructors take on a little bit different significance in agents than they have in classes. That's really where sort of you can run, you can have your entire lifetime of your agent in the constructor if you want. OK, I'm going to skip the part where I generate an error. Well, actually, I'm not going to skip the part where I generate it. I'm going to try to compile this. And we're going to see that the compiler does not think that my code is behaving properly, because as I'm updating the dictionary, I'm actually writing domain data. And the compiler says that I cannot do that from a no-access agent. Agents are no-access by default. I have to actually increase. I have to be explicit about increasing their privileges. In this case, it needs to be a writer, because it has that put. OK? And this time, it's going to work. And this is the gun, right? No, it's not, actually. Sorry. This is the lock. I'm going to talk about the gun later. I'm going to go back to I'm going to put something. I'm going to put my hosting code in the constructor of the domain. I talked about this earlier, right? And here we have something called an in-proc host. That means that this is my way of doing efficient local hosting. And then I'm going to, up here in my main program, I'm going to create a connection to this table agent. And I'm going to put a few messages in, a few values into it. And I'm going to retrieve one and see what happens here, right? So I'm associating foo with A, bar with B, I think it is, and stop with C. And I'm going to retrieve A and see what we get here. Foo. OK, so I got foo back. That's very, very interesting, isn't it? So we'll stop here, if I can find stop. Stop debugging. I'm going to now, so now this was just my main program, putting something into a table and retrieving it. It's not that cool. But what I'm going to do is I'm now going to create another agent that's not my main agent. It doesn't share any data with my agent, because they're not in the same domain. But I'm going to have it access this same table. OK, so first I need a simple channel to communicate with my second agent. All right, it's really a brain dead kind of channel. Just says start and stop, essentially. My second agent also is not part of any domain. It lives out in the free, so to speak, and therefore has very few privileges. But what it does have access to are addresses, right? And that's where it's doing its connection to the table through an address, in this case foo, which is the address that we used in the host statement we saw down in the domain constructor right here. Okay. So if I put a breakpoint there, we should be able to see what we've gotten out of the table. Now, I need to actually also add some code up here to create the second agent from my main program, from my main agent. This thing is kind of interesting. This is a very, very simple data flow network where I'm taking the done signal from my second agent, and I'm forwarding it to the main agent's done port, so that when the second agent is done, the first agent is done. It's going to wait for the done signal from the second agent before terminating. And so I need to comment out this other thing here. OK, so I'm going to run this. I'm going to try to retrieve this value. OK, and what did we get here? We got stop. OK, so this will get a little bit more interesting when we're doing this distributed. But the idea here is that, again, if I can find stop, the idea is that I am doing, without actually having any access to that actual data, not by reference, not by anything, I can now share it between two. And I have an arbiter there. That's the domain that is giving me safe access to the data in there. I'm having to copy it when I'm going in and out. But that's the price to pay for a safe concurrency model. Now, if I was passing immutable data in there, like strings, in this case are, key value pairs aren't, I believe. But strings are. So if I was just passing strings, they could be passed by reference because they're safe, right? I'm going to move back to the presentation here and go into no. There we go. I'm going to go into, helps if I change the switch to it also. There we go. I'm going to go into where we have a gun, right? So we have schema. That's really kind of like a record definition. It's not a class. It doesn't really have methods on it. It doesn't have behavior. It just defines data payload, right? But it has this thing also that, in addition to fields, it has this thing called rules, right? And they say, if you're going to send me data, it has to look like this. It has to obey these rules. And the reason I want to do that is I want to catch the error at the source. This is particularly important when I have asynchronous messaging, because the sender sends erroneous data, moves on, the receiver validates the data and says, this is wrong. I'm going to send you an error message back, but the sender has moved on, right? He doesn't have necessarily the context, and he may have taken actions assuming that the data was correct. So he needs to be notified right away that it's incorrect. So that's the gun. Like, shoot it down right away. We're going to take and add a schema to our application. We're going to replace this. No, that's not what I meant to do. We're going to replace the key value pair with the schema table entry that says you cannot send null values or empty strings. And I need to replace table entry replace this in 3 places. And I'm going to send invalid data here. And I'm going to do one thing here. Sorry, I should have set this up in advance. I'm going to go down to debugging and do enable just my code. Okay. So I'm going to send invalid data to this guy who really, really doesn't want any null strings. And we'll see what happens here. Or we'll see what happens when I press that. OK, so the line reporting here is a little bit off. That's a fault in the Axum, Axum language service. But not only do we get an exception, we get an exception that actually says exactly what the condition that was violated was. So we get validation at the source. This never made it into the table. This never made it into the agent servicing the table. This was caught at the source. OK, I understand what this is now. OK, now. OK, now, I can also do something, if I can find my pointer. I can also do something very similar on the channel definition. We can add something that's called protocols. It's a little bit more sophisticated than rules in that I can not only define what the payload must look like, and if I have payload definitions on my schema, I can further customize it for particular uses in a channel, but I can also define the legal order of messages. It's saying that sending this message before that message just doesn't make any sense. Like sending put after done, that really is not what we agreed on doing here, right? You were supposed to send done when you weren't going to do any more messaging with me, right? I'm going to skip the example of adding protocols to our schema because we're a little bit behind. Data flow networks, send and receive are very powerful constructs. It's hard to combine asynchronous code. It's hard to combine these types of messaging primitives with control flow unless you have what looks like blocking constructs like receive. Right? It's very, very hard. That's one of the hardest things about the APM, for example, or any of the other library-based approaches, is doing them in while loops or if statements and whatnot, right? Doing multiple of them after each other. That's hard. So we need some kind of blocking constructs, but they're not always the right solution. They can be more expensive than the callbacks. So what we define then is we have something we call data flow networks, and they're kind of a generalization of the callback method, if you will. What it does is it propagates data between computations, buffers, and ports. And we do this using an expression syntax that is unique to Axum, if you will. So we're not doing this with library calls. You could, but it looks it looks better and it's more readable, we think, if you're doing it with infix operators. So for example, I have the first example here, and we have some operators here. We have like a forwarding, which is a pipeline. That's our first example, is a pipeline between two ports and a transformation function in the middle. The second one is a multiplex, or actually it's a broadcast. It takes the things that are coming on the buffer and broadcasting it to an array of operators. Operands, I mean. Okay. Here's what ping pong, our first example, would look like with a data flow network. I said, remember the ping pong really didn't do anything interesting. It just looped around and did nothing of interest. So that's a particularly simple one. We don't need any control flow to orchestrate the trivial logic of ping pong. We can do it with a data flow network. It's fantastic, in fact, for this. It's more readable, I claim, and it's actually going to be more efficient. I don't have to use a lambda like I did in the previous one. I can put in methods also, of course. But sometimes you really want to use receive. You really want to use message passing, and you don't want to use data flow networks. They're not good for everything. But then you have to deal with the technology scale issue that I was talking about earlier of synchronous protocols. So if you look at receive, these three, we say while receive, it looks extremely blocking, and it is blocking in a logical sense, right? At least. If you also do it in an actual sense, which you typically do when you are implementing things yourself in library code without the help of a compiler, then you're going to be holding on to a thread. It doesn't matter if you created the thread yourself, if it came from the thread pool, whatever it was, you're holding on to a thread. That's expensive. On .NET, there's at least 1 megabyte of memory held for the stack. It allocates kernel objects, right? And any context switching between threads is done via syscalls into the kernel. Very, very high overhead, right? We don't want that when we're trying to write parallel code. We're trying to not waste time, going across rings on the hardware. We're trying to spend our time and energy, by the way, right, on computation that does something for our program. The asynchronous ABIs that are in existence are very runtime efficient. They keep the state between, before the wait and after the wait in the heap instead on a stack. But as I said, they're complex to use in program code. Right. So the Axum approach to this is to have the compiler do the work for you. Right? This is more of the grandma approach, actually helping you, enabling you, rather than telling you no. But it is still something very valuable that the compiler can do. And I have an example here. I'm going to switch to using that. If you want to see the distributed table running distributedly, come up to me afterwards and I'll show you that. It does work. I ran out of time showing you that. So if we look at this example, I have a trivial little agent, and its only point in life is to block, so I can demo my point. So I can demonstrate my point here. And I'm going to start these. I'm going to create a number. I have 25, actually. I'm going to create those. I'm going to send them. I'm going to wait for them all to tell me that they have started. And then I'm going to block with a read line. And then finally, I'm going to tell them that you can go away now. So they're all going to be waiting for done, right? And I'm going to bring up the task manager to study what happens when we do this. OK, so it's going to be it's going to come up here. Actually, it comes up over here. And it's waiting for me to hit enter, which I will comply with. And then I'm going to bring task manager forward again. OK, so async agent here, it's growing threads. Actually started with almost 10 threads. I don't know why the runtime adds that many. I started 25 agents. I wound up with 35 threads, right? Now, it would be, I could have done 50 here easily. I could have done 100. I could have done 500. But it gets interesting when I try to do something like 25,000, right? We don't have time to wait for that, because creating 25,000 threads, first of all, it will completely bog down the system, and it will just quit after about 2 or 2,500 threads or so, because it's a 32-bit system, and I will simply run out of address space. I will simply run out of address space. However, what Axum does, and I disabled this compiler feature just to demonstrate here, but what we have in Axum is we take care of this by doing the asynchronous transformations that you want to do for you. I'm going to rebuild this with this asynchronous agent constructor property set to true, and see what happens. I'm going to run it. Hopefully it pops up on the right screen. No, it doesn't. I'm going to hit enter. And we can see what happens. I started 25,000 agents, and I added 1 thread. OK. Now, I can scale this to 1 million agents, and it actually takes a little bit of time, so it's not interesting. I can do this, and they're all blocked, just like they were before, but they're doing so asynchronously, and the compiler takes care of it for you. All right. So this is some of the value of having the compiler do work for you. This is why language integration is actually interesting and does more than what you can do with just framework-based solutions. All right. So agent-based programming is not something that we invented. Here. Nope. Let me talk about Erlang. It's a purely functional language, pure message passing, gets isolation through relying entirely on immutable types. Scala has agents. It's functional. It runs on the JVM. Their agents aren't isolated, but they do have some immutable types. Distribution is a separate model. So this is a model that focuses on in-process agents. Right? And it does have some basic support for asynchrony. F#, shipping in VS 2010, focuses on in-process agents. It is the place, in my opinion, to start with agent-based programming. And what Axum one way of looking at Axum is that we build on those concepts and take them to add isolation, add channel-based communication, and add an integrated distributed model for it. OK. I am going to show you what agents looking like in F#. There's a type called mailbox processor. It's really a queue that you can hook up a callback to. And that callback then, in effect, becomes the agent. In this example, and this is the asynchronous, this is the 25,000 thing, right? I'm going to do 50,000 here instead. But in this example, I use 2 mailboxes for this agent. I use one for the inbox, data coming into the agent, and one for the outbox, data going out from the agent. OK? Right, so it looks like this. I'll not run it because we have some other things to talk about also. But I find it rather interesting that if we look at all these 3 that have agents, one thing they have in common is that they're functional languages. So that kind of piques my thinking about whether a C-based syntax that we chose for Axum is the right place to start. Maybe it is the case. Well, of course, syntax. You can have functional. Scala is a C-based syntax too, right? And functional. So it's not really just the syntax, but the idea of starting with a mostly imperative model and winding up with agents might not be the right solution. Maybe functional programming languages are closer to our model than not. And in fact, that's my conclusion, is that the Axum model is a closer fit to F# than to C++ or C#, at least in their current incarnations. There are a couple of things that suggest this, to me at least, right? And one is that F# does have immutable types. It has an immutable subsystem of the .NET type system. It does have support for asynchrony. And in fact, Luke Hoban, who's a PM on the F# team, in half an hour or 36 minutes, is going to have an entire session on F# parallelism and asynchrony. And I strongly encourage you to stick around for that session. It's going to be very, very interesting. And it's going to tell you things you can do today with VS 2010 Beta 2 that you don't have to wait for Axum to do. And it does already have an in-process agent API, so we can start getting some of those patterns together and start getting them used and make them mainstream. You just have to add channels, isolation, and schema, and you really have Axum. It's that close. No, I'm not going to go to the summary just yet. I want to show you something that we've been working on. We put the Axum CTB out in May, and we had an update in June for VS 2010 Beta 1. Since then, we have been working on prototyping the Axum concepts in the F# syntax. And I just want to take a second here and show you what that could look like. So we do introduce channels. I don't know how many of you are familiar with F# or its syntax, but I just want to sort of contrast this with this here. We do define channels, and they are channels just like in Axum. In other words, they're copying if it's passing references if it's safe. They support distribution. Agents are explicit, and agents need to be explicit so that we can have the compiler slap us on our hands when we're doing the wrong thing, right? Actually enforce isolation. So channels are there to support the distribution and message passing, and agents are there to do isolation. And rather than having domains and agents as different syntactic constructs here, what we're doing is we're actually having agents and nested agents. So an outermost agent becomes a domain from a pattern perspective and acts as it, but it's still just a domain. OK. I have a little bit larger example here. This is a variant of the distributed table. And here you can see that I'm actually using two nested agents. The other one acts as the domain. That's the one called table. And the inner one acts as the proxy, or the agent that we had in our previous example. All right. And they're all relying just on the F# support for async workflows, which Luke will talk about in great detail next. We have hosting just like in the Axum like we saw before. And yeah, this is what it could look like. I'm very excited about the sort of the possibilities that functional programming has. I know that it's kind of a uphill struggle, perhaps, to make functional programming mainstream, but it's at least interesting as a thought experiment, I think. So in summary, shared memory, complexity, both from a perspective of the hardware, which has a hard time dealing with a cache coherence traffic resulting from false sharing and other things like that. But also from a process perspective, and that may be even more important, right? Because that's, to some extent, that's just raw cost, right? Raw cost to an organization building software. Pure message passing, like some languages use, unless you're building it on purely immutable data types, it has a high overhead. So it's not for everything. It really shouldn't be used for everything. We need to limit the amount of message passing we're doing. Axum tries to balance message passing, which is sort of the basis for safety here, and shared memory access to state. And it does it through a declarative model, which allows us then, and this comes back to one of the very first slides, which is that we want to leverage existing things. And we can do so within the agents. We can call libraries, object-oriented libraries. We can call anything in .NET, really, as long as it doesn't access globals, which very few actual libraries do in an unsafe way. And that allows us to, again, use a special purpose language for the higher levels of our architecture, our code, and build on existing know-how, build on existing patterns for the bulk of our code. It's still available on DevLabs, so please download it, try it out, tell us what you think, tell us what you hate, tell us what you love. Tell us, even if you don't try it and find it immediately useful, tell us what you think it could be useful for. Tell us what you would like to see added, because it's almost there. Not quite, but almost. And get involved with that. We have a blog, a Maestro team. Axum used to be called Maestro at one point in the past. But there's also a forum on DevLabs that is more interactive, perhaps. There's a number of parallel computing sessions at PDC 09. And one of the more interesting right now, today, I think is coming up right after this. And that's the talk on F# and parallelism. I think you've seen this slide before, but please fill out evaluation forms. And catch us on Channel 9. I've run out of time here. I will be available at the podium for questions from anybody who is interested in hearing a little bit more. And thank you for coming.